أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. اليوم عندنا موضوع خاص ب design of heat exchanger. And this is actually part of MEP 460 heat exchanger design, which is offered in Mechanical Engineering Department, King Abdulaziz University. Our focus for this presentation will be sizing steam condenser with a solved example. The contents of this presentation will be a brief introduction about phase change heat exchanger like evaporator or condenser, and then we'll give a statement of the problem and all the input data and what is required. Then we give the procedure to size the condenser. After that, we give a flow chart describing the step-by-step procedure to size the condenser. After that, we will give an expression or some more information about calculating the pressure drop for such heat exchangers. Then after that, we will give some conclusions about what we have found from solving this example, and we conclude with some list of references regarding this type of heat exchanger. We know that category of heat exchanger, we call it phase change heat transfer equipment, where evaporation or condensation take place. We know that condensation and evaporation is characterized by very high heat transfer coefficient. In addition, condensation and evaporation usually takes place at a constant temperature. For example, if you are talking about condensation, then you are talking about converting the phase of the fluid from saturated vapor to saturated liquid. For the evaporation, you are going from saturated liquid to saturated vapor. Here we are considering a condenser with no fin, so it is unfinned condenser. In order to understand the process for condensation and evaporation, this diagram actually shows the condenser temperature variation, and here we see also the temperature variation for the evaporator. Assume that we have a condenser that is condensing at constant temperature, and in the other side of the heat exchanger we have a fluid that is raised, the temperature is raised from state here at the inlet up to a temperature at the exit. So the heat is transferred from the condenser, T condenser, to the fluid. Since the condensation takes place at a constant temperature and the specific heat is defined as partial H by partial T at constant pressure, since the temperature is constant, so the specific heat is as if it goes to infinity, very high value. So C minimum actually is this value for this fluid, which is the product of the mass flow rate times the specific heat. So for heat exchanger, for a condenser heat exchanger, C min divided by C max actually is 0. Since CH or here, which is the hot fluid, goes to infinity, and C min for this fluid, which goes from this temperature to this temperature, which is C minimum, so C minimum divided by infinity, so is 0. So for the condenser as well for the evaporator, the C min is equals some value for the fluid, which is either increasing in temperature or decreasing in the temperature, and the specific heat for the other fluid where you have a phase change, either condensation or evaporation, is a very high value. So CR, which is the ratio of C min divided by C max, is equal to 0 for both condensation and evaporation. Notice that condensation is a constant temperature process. So the fluid enter at saturated, for example, vapor and leave as saturated liquid. Here it is saturated liquid and leaves as saturated vapor. But the heat actually is transferred from the high temperature to the low temperature for the condenser and for the evaporator. The effectiveness NTU relation that relates the effectiveness and NTU for phase change heat exchanger is given by this equation: epsilon equal 1 minus e to the power minus NTU. Or if you would like to find the NTU is minus ln 1 minus epsilon. So this is a very simple relation that relates the effectiveness in NTU. Of course, CR is not appearing here because CR is 0 for both a condenser or evaporator. The statement of the problem that we are looking for is given in the Arabic book. It is problem number 9.11 in the book, and the basic idea is given some information in order to design a condenser so that you find the size of the condenser. We are giving the following. We are giving the inlet temperature of water that is coming into the heat exchanger at temperature at 25 and leaves at 45. The condensation temperature is 110. The mass flow rate of water is 100 kilogram per second. The inlet, the inside and outside diameter of the tube is given as these two values. Sigma, which is the area of free flow area divided by the frontal area, is assumed to be 0.5. The bulk pressure drop, the maximum pressure drop between the inlet and exit of the water, is assumed to be 20 kilopascal. The heat transfer coefficient outside the tube, the condensation, is 18,000 watt per meter square Kelvin. The thermal conductivity of the tube material is 60 watt per meter Kelvin. We also sometimes, if the problem gives some value for the what you call it pressure loss coefficient at the entrance and the exit, which is Kc and Ke, Kc at the entrance and Ke at the exit, here we are going to assume two values, but actually not going to include them in the relation. So they are here but just to show that if somebody would like to take the exit and entrance pressure losses, it can be taken into account. Sigma, as we said, defined as the free flow area divided by frontal area, and this is the free flow area and the frontal area. The required for this example or the problem is to find the length of the heat exchanger. How much is the length of the heat exchanger in the direction normal to the paper, and the number of tube needed in order to condense the steam at 100 degrees C, and also to heat the water from 25 degrees up to 45 degrees. We are going, as I said, we are going to neglect the pressure drop due to entrance and exit. We are going to focus only the pressure drop due to friction in the tube only. This is the cover of the Arabic book from which we have taken the problem. Problem number 9.11. This book actually is in Arabic, and it is called Heat Exchanger Design, and it is offered or published from King Abdulaziz University. This is the statement of the problem 9.11 from the book itself, which is actually exactly what we have seen about the inlet temperature, the outlet temperature, the other data that we are focusing on. Now, to start the procedure of sizing the condenser, first of all, we calculated the average temperature, which is 25 plus 45 divided by 2, so it is 35 degrees C. And we calculated the properties of water at this temperature: the density, the specific heat, the viscosity, the thermal conductivity, and the Prandtl number. Since we know the mass flow rate of the water and also the specific heat of water and the temperature difference, we can calculate the Q, the amount of heat, which is going to be 8358 kilowatt. We can also calculate the Q max, which is C min multiplied by delta T max, and it's going to give us this value, which is 35.521.5 kilowatt. If you divide the heat rate by the maximum heat rate, you get the effectiveness, which is 0.2353. Then actually using the relation that relates the effectiveness and the NTU in this equation, since we are having a phase change heat exchanger, we can calculate the number of transfer unit. It's going to be 0.2683. Now, For the case that we have in hand, we have condensation over the tube and we have convection inside the tube. So actually the heat transfer coefficient for the condensation is much higher than the heat transfer for the flow inside the tube. We can relate the number of transfer unit for the whole heat exchanger to number of transfer unit inside the tube. For this particular case, actually, since the thermal resistance of the flow inside the tube is higher than the thermal resistance for the condensation, we are assuming that the thermal resistance for the flow inside the tube is the resistance is 10 times the resistance of the condensation on the surface of the tube, from which actually we can get this relation that relates the number of transfer unit for the flow inside the tube to the number of transfer unit for the whole heat exchanger. Of course, the number of transfer unit for the flow inside the tube is equal to the heat transfer coefficient for the flow inside the tube times the area, the heat transfer area, divided by C minimum. From which actually we can find the number of transfer unit for the flow inside the tube, 1.1 multiplied by NTU for the whole heat exchanger, so we will get 0.29513 for the number of transfer unit for the flow inside the tube. As I said before, the internal resistance, convective resistance, is inside the tube is much greater than the condensation resistance over the tube. And in order to understand this, the basic source of this equation, there is another video for sizing gas-to-gas heat exchanger. You can go to this site and or link and see the sizing of gas-to-gas heat exchanger, where we also deduce another relation that relate the number of transfer unit for the gas side, for one gas side, to the number of transfer unit for the whole heat exchanger. Now this is the same thing actually. We are considering a gas-to-gas heat exchanger, for example, and we would like to relate NTU1 and NTU2 to NTU for the whole heat exchanger. So if we consider two gases in series, one of them the resistance is Rg1 and the other one is Rg2, and we are assuming they are of the same order since they are both gases, you can actually relate the number of transfer unit for this gas by using the NTU for the whole heat exchanger. For this case, we are going to get NTU1 equal to 2 NTU for the whole heat exchanger multiplied by C min divided by C1. And the same thing also for number of transfer unit for the second gas, since they are gas, so they are of the same order. For the case if we have a liquid and a gas, we know that the resistance for a gas is much greater than the resistance of the liquid. And so actually we can go back and substitute and find out how much is the number of transfer unit for the gas in terms of the number of transfer unit for the whole heat exchanger. It's going to be 1.1 NTU for the whole heat exchanger multiplied by C minimum divided by C gas. And for the number of transfer unit of the liquid side is going to be 11 NTU multiplied by C min divided by C liquid. What we have actually in this particular situation for the condensation, the resistance of the flow of the liquid inside the tubes is much greater than the convective heat transfer, or the resistance for the condensation of the tube. So this one is greater than this one. It's 10 times much greater than this one. So we can get also the relation that relates the number of transfer unit for the flow inside the tube with the number of transfer unit for the whole heat exchanger. So this actually what we are assuming in this particular case for the condensation. So the number of transfer for the flow inside the tube is going to be 1.1 number of transfer of unit for the whole heat exchanger multiplied by C min by C gas. But C min is the same as C for our case, C liquid, which is the flow inside the tube. So the number of transfer unit inside for our case is going to be 1.1 multiplied by NTU. The definitions for NTU total and NTU1 and NTU2 are given by these expressions here for the whole heat exchanger, for side 1 and for side 2. We continue now the procedure for sizing the condenser. We need to start with the value for the mass velocity, which is G, which is the multiplication of rho times V. Again, if somebody interested to know this, the derivation for the equation that we are going to see later for finding an estimate value for G, please go to that video which is entitled sizing gas-to-gas heat exchanger. The basic idea actually is we start with this equation that relates the pressure drop in a pipe or in the flow, either for any flow that we have. Here we have a flow inside a pipe. We know that the pressure drop actually due to many things, but the major thing is the friction in the pipe. So the pressure drop actually is equal to 4 times the friction coefficient multiplied by the ratio L over D multiplied by G squared divided by 2 multiplied by the density. If you take G to the right hand side, you can get G in terms of the other parameters here. But in order to do that, actually we need to find a relation between the heat transfer coefficient inside the pipe with the NTU that is for the whole heat exchanger. So we have to found out that for the particular case that we have here, since as we said the resistance for the flow inside the tubes is much greater than the resistance of condensation on the outer of the tube, so NTUI equals 1.1 NTU. So actually we can relate H, the heat transfer coefficient inside, with known thing which is NTU. Also we can write an expression for the ratio L over DI in terms of the heat transfer area and the free flow area, the minimum flow free area. We know also that the heat transfer coefficient can be written in terms of Colburn modulus. So actually we can write Colburn modulus, the heat transfer coefficient actually in terms of the Colburn modulus and G plus Cp and Prandtl number. If you take these three equations and substitute, you will get an expression for G, which is shown here. So G is actually some terms between two brackets, and between a bracket, to the power 1/2, where delta P max is the pressure drop inside the tube maximum allowed by the statement of the problem. Prandtl number is known, NTUI is known, and then we have the ratio of Colburn modulus divided by the friction coefficient. We are going to assume a value for this. Hodge book, where he assumed actually G over FC equal 0.4, but actually, as we're going to see later, you can assume different value for this ratio that satisfy the situation that you have in hand. Anyway, we are going to use this expression for G in order to find a very initial value for G to start our iterative procedure to find the size of the heat exchanger. We are assuming that J over FC is going to be 0.4, as we are going to see later, and going back also to the same thing that I recommended earlier, that you go to the gas-to-gas sizing video in order to understand more about the derivation of this equation. The ratio of the Colburn modulus divided by the friction coefficient is shown in this figure, which is taken from Case and London Compact Heat Exchanger book. And in this figure, which has been also explained in the gas-to-gas sizing compact heat exchanger, we have Reynolds number in the x-axis, and in the y-axis we have the ratio of Colburn modulus divided by the friction coefficient for different geometries. In our case, actually, we are going to assume the same value that has been assumed by Hodge in his book, that is J over FC equal to 0.4. For finding initial value for G, the ratio of JH by FC is taken to be 0.4 in our situation. once you substitute with the 0.4 for this and substitute the values for the other parameters, you can get a initial value for GI, which is, for this case, it's going to be 4,339 kilogram per meter square second. Now, once you have this value, you can actually find the Reynolds number, and also you can find the Nusselt number using the expression for Nusselt number given by this expression for turbulent flow, since we are having a turbulent flow here. Reynolds number is 1.16 to the power 5. Calculating the Nusselt number, this value, and then you can calculate also the heat transfer coefficient, which is going to be, after substituting the value, is going to be 13,300 watt per meter square Kelvin. Now, since we have H inside and we have H outside for condensation, we can calculate the overall heat transfer coefficient, adding the resistance of the wall of the tube. So we have three resistances: the resistance inside the tube, the resistance outside the tube due to the condensation, and the resistance due to conduction in the tube. Once you substitute the values, actually you can find out that the overall heat transfer coefficient for this particular heat exchanger, assuming initial value for G, this value, you can get the U value, which is 5884 watt per meter square Kelvin. Now, with this value, actually, and since we know NTU, because we have calculated NTU at the beginning of the problem solution, so we can use this and UI, of course, we have found the value of UI, the overall heat transfer coefficient, and we know C minimum. So actually you can calculate the heat transfer area for the flow inside the tube, which is going to be 19.1. Also, you can calculate the area based on the outside surface if you want to. We know that the G is not more than the mass flow rate divided by the free flow area. So actually we can, since we have G and we have also M dot, we can find the free flow area, the whole flow free area, which is going to be 100 divided by 4,339, which is going to be 0.023 square meters. Now this is the area of the flow for the whole heat exchanger. But we know that for a single tube, the cross-section area is pi over 4 di square. So it's going to be 5.56 10 to the power minus 5. If you divide the whole area by a single cross-section area for a single tube, you can find N, which is the number of tube required. If you divide 0.023, the total free flow area, divided by a single tube cross-section area, you get 42, about 42 number of tubes. Also, since you know that the area, the heat transfer area is pi dl times n, so actually you can find L, the length of the heat exchanger, which will be 5.4 if you divide the whole area, 19.1, divided by pi di multiplied by n, which is, we found it 42. So now we came to the conclusion, but after assuming an initial value for G, we found out that the number of tubes is 42 and the length of the tube is 5.4. So as if we size the heat exchanger now. But how can we tell that this is true, this is okay with with the requirement of the problem that delta B has to be 20 kilopascal? So what we have to do is to check and find out how much is the pressure drop. We have to differentiate between friction factor and friction coefficient. Of course, the friction factor actually is 4 times the friction coefficient. We are going to assume, assume that the flow in a smooth pipe, and we use this relation that gives the friction factor as a function for Reynolds number for turbulent flow. We will get the value of 0.0163 as a friction factor. Then we can go and substitute in this expression to find the pressure drop, actual pressure drop, how much, and we found out that the pressure drop is 31,000 something Pascal, which is much greater than 20 kilopascal required by the problem. So the percentage error between the two values, we take the actual value minus the pressure drop required, divided by the pressure drop also required, multiplied by 100, so you get 56.7. So the pressure is much greater than the allowable pressure. Now, since this is not satisfying the problem statement, the problem requirement, then we have to modify our G value. So what we do actually, we use the same expression for G. The only thing that we substitute delta B as delta B max, which is the required pressure drop. In addition, the friction factor also and the length of the heat exchanger, we use the previous value of what we have found from the initial guess of the G value, which is the mass velocity. If you substitute now with delta TB max equal to 20,000 and a friction factor with the value that we found earlier and the length of the heat exchanger, which is about 5.5, you will get a new value for G. Now once you get a new value of G, you can proceed and go ahead and find out the Reynolds number, the heat transfer coefficient, the overall heat transfer coefficient, the heat transfer area, the number of tubes, the length of the heat exchanger, and delta B actual, and see how much is delta B actual is different than delta B required or delta B allowable pressure drop. We did that through using a MATLAB, and this is the second iteration, the second iteration for finding out the size of the heat exchanger. So this is the Reynolds number, Nusselt number, heat transfer coefficient, heat transfer area, free flow area, number of tubes. Notice that we found it around 42 in the first case. Now it's going to 52. The length of the heat exchanger also changed. Delta B actual has been changed also, 1.8 10 to the power 4. The difference between delta B actual and delta B required multiplied by 100 actually is, for this case, it's going to be minus 10%. You can proceed now and find another value for G, and you do the same thing calculations again. You will get more closer to the delta B actual every time you do the iteration. You continue this process of finding new G and finding new values for all the parameters until you get how much is delta B within what we call a conversion criterion that satisfy your requirement as a designer. This is a flow chart showing the process in summary. We start with all the information that is given about the fluid, the temperatures, and the allowable pressure, and then we use another subroutines to find how much is the thermal physical property like density, specific heat, thermal conductivity, and so forth. And then we calculate how much is Q for the heat exchanger, how much also the maximum flow rate, and also how much is the effectiveness, and also how much is NTU as we did before, and NTUI, which is the NTU for the flow inside the tube. And then we have to start with a value for initial guess for the mass velocity G, and from which actually you can find the Reynolds number, and you can find, of course we are assuming typical value for the friction, for the heat transfer divided by the friction. We took it 0.4, but you can take another value if you want to. Then knowing G, actually you can find the Reynolds number and the friction factor and the Colbrand modulus, from which you can find the heat transfer, from which you can calculate the overall heat transfer coefficient, and then you find the heat transfer area. Then you can calculate also the free flow area and the number of tubes that is required. And after that, then since you know the heat transfer area and you know N, you can calculate L, the heat exchanger length, how much. Since we know that the area for the heat transfer inside the tube equal pi times d times the length times the number of tubes. Once you get the number of the length of the heat exchanger, you can now go and proceed to find the pressure drop, actually how much, using the calculated values for the length of the heat exchanger and the friction factor that you found. Then you find out how much is the difference between delta B actual and delta B required by the statement of the problem, and you put a value, the tolerance between these two values, so that you can either stop or go and calculate another value for G using the same previous values that you found for the length of the heat exchanger, the friction factor, and so forth. So actually the process of going back to calculate a new G is basically based on how much is the tolerance between delta B actual and delta B required by the problem. And the procedure actually here is a very systematic, since you are going to, after finding G, you have to calculate the Reynolds number, friction factor, Colbrand modulus, the heat transfer coefficient, overall heat transfer coefficient, the area, and then the length and the number of tubes for the heat exchanger, and delta B again. We would like also to say a few things here about the pressure drop for this or similar heat exchanger. The pressure drop actually, according to the book of Case in London and other resources, for generally it can be written in terms for as a summation of the pressure drop. Actually is a summation of 4 parts. This part they call it entrance region, the entrance of the heat exchanger, which, as you can see, is a function of sigma. Sigma actually is the free flow area divided by the frontal area, and Kc is a pressure drop coefficient for the entrance only. The second term is acceleration, and as you can see, the difference between the density inside and outside has some impact on the acceleration part of delta B. The third part is very well known, the friction, due to the friction in the wall of the heat exchanger, which is, as we said before, the friction factor times the ratio L over D multiplied by rho I and rho M, and then actually multiply by G square here in the front of the bracket. The fourth part is the exit pressure drop, which is a function of the densities, the coefficient for the flow exiting the heat exchanger, and sigma, which is, as I said, the frontal area, free flow area divided by the frontal area. So we actually call this term T0, and we call this term T1 in our MATLAB program. This is T2, this is T3, and this is T4. And within you, in order to find a delta B, then you have to T0 and then a bracket where you have T1, T2, T3, and T4. Remember that the friction factor is actually 4 times the friction coefficient. These parameters has been again said what is each one of them represent. Actually, Shah in compact heat exchanger design, which is a heat exchanger thermal hydraulic fundamental and design book, 1981. Shah has a separate condensed very good paper about compact heat exchangers, where this has been explained in more detail. In addition, this figure actually is from also the same source, where we have 4 geometries here for finding Kc and Ke, where Kc, as we said, for the entrance coefficient of a pressure drop, and Ke is for the exit from the heat exchanger. So this is the exit and entrance, actually based on how much is the value here in the x-axis, sigma. So you have different curves for either laminar or turbulent flow for different geometry. This is flow inside. This is flow inside the tubes. This is some other geometries for gas to gas, or gas to gas, and gas to liquid heat exchangers. This is again the same reference from which we took these figures. Now, to conclude, actually, for this particular example or problem that we solved, we can say that actually is the problem is much simpler than gas to gas sizing heat exchanger. But here actually just a condensation on one side, and the other side we have a convection or a flow of fluid or water inside the tube. We are of course all the input data is given, including the temperature of condensation, the inlet temperature of water, outlet temperature of water, the heat transfer coefficient for the condensing side, in addition to the flow rate and the temperature inlet and outlet. It is required to find the length of the heat exchanger and the number of tubes that is required, subjected of course to the delta B maximum, which is for our problem 20,000 kilopascal. The procedure has been illustrated, and we started the procedure, the iterative process by assuming initial value for the mass velocity, and then after that actually the process is easier and can be carried out by a program like MATLAB. Actually, I have done two programs, one using two iterations, and the other one actually solving the same problem using if-solve, because if-solve actually it will iterate until you get the answer that is required. References for used for this particular type of problems, we use of course the compact heat exchanger chapter that done by Shah in the book of heat exchanger thermal and hydraulic fundamental and design by Kakaj and others, 1981. Of course the new book fundamental of heat exchanger design by Shah and others, 2003 also, it has some information about such heat exchanger. Hodge actually book Hodge and Taylor analysis of design of energy system has a section about heat exchangers, and they have a very similar example for solving a condenser design problem, very much similar to what we did. We have changed some of the parameter values, but actually the idea is there, and it's solved by using MathCAD. We solve it by MATLAB and by hand also manually. Of course we need Incropera for the properties of the fluid and the relation between NTU and effectiveness, and basic method for heat exchanger design. Walillahi alhamdu wal minna. We can go quickly to show you two MATLAB programs. This is the first program in MATLAB where we put all the input data that is given, and we find also the properties using some other subroutine, and we find how much is NTU and how much is Q and Q max and so forth, as we did in the explanation, and we assume certain value for the ratio of J divided by the friction coefficient. And we started the first initial guess for G, and then we proceed with Nusselt number and so forth until we get how much is the length of the heat exchanger and how much is delta B actual, and compare it with delta B required. And also we go to another value for G, assuming using the utilization of the first result from the first initial procedure. And we find G2 and so forth. So actually when you run this, actually you get two iteration for finding the length and the number of tubes. So if you go here, you'll find that L actually this is L, the final value is 4.74 meters, and the number of tubes actually in 3 here is around 52 tubes. And if you compare the delta B actual with delta B if you compare delta B actual with delta B required, delta B actual is for the third or the second iteration actually 1.8 10 to the power 4, which is, as we said, very close to delta B actual, which is this value. Of course, all the parameters are there. If you want to, if somebody would like to see all the parameters, for example, G initial value, G second value, and third value, and so forth. This is what is solving the problem by hand, as if it's by hand, with iterations. But also we did another program utilizing what we call the if-solve, which solve the problem and find how much G. Of course, you need initial value for G, but for iterative process, the if-solve actually is iterating the value of G until you get the final conclusion. So if we run this again, this is now solving utilizing if-solve. So if you run this with the same, almost the same actually the same input data. The only difference is that we put some kind of a KC and KE for, if you go here back, we put some kind of a KC for the entrance of the heat exchanger coefficient, and the same thing for the exit KE. And so if you look and find how much is G, the final value is this one, and the number, the heat exchanger length, is 4.9 meters, and the pressure actual is almost the same as the pressure required, which is 20,000, as you can see here. And all other parameters, the heat transfer area and everything is also listed here, in addition to all the calculation that has been done. We are using here, if somebody would like to utilize if solve, this is actually the command that is utilizing all the information given, and we use what we call sizing condenser function, which with input values, and this is the initial guess for G. So if solve actually in this will go and solve the problem. Of course, the problem had these H, capital H, C, H, X, W, and X these are all the input information that is required. If you go to this function that calculates actually how much is the difference between delta B actual and delta B required in each time. But if solve will try to utilize this function in order to get zero difference between the two.